Hello everyone, this is Dr. Vandana Malviya from SS College of Engineering, Udaipur. In this video, I am going to discuss the solution of homogeneous linear differential equation of second order with variable coefficient. First of all, what is the type of homogeneous differential equation? This is the homogeneous differential equation, equation number 1, a0 x square d2y upon dx square plus a1x dy upon dx plus a2y equal to q, where a0, a1 and a2 are constants and this right hand side q function is of x, or maybe it is constant. So this equation number 1 is known as homogeneous type differential equation. For solving this type of differential equation, we have this assumption x equal to e raised to the power z, or we can say we can take z equal to log of x. From this substitution we have to calculate now dy upon dx and d2y upon dx square. Simply by differentiation we are calculating this term dy upon dx, and after differentiating in equation number 2 we can see we are getting x dy upon dx equal to dy upon dz. Similarly, we have to calculate d2y upon dx square, and after again differentiating we can get the value of x square d2y upon dx square as d2y upon dz square minus dy upon dz. If I am taking d by dz as capital D, we can replace x dy upon dx as capital Dy and x square d2y upon dx square as d minus 1 y. So these are the substitution. In place of x we have to replace e raised to the power z. In place of x dy upon dx we have to replace dy, and in place of x square d2y upon dx square we have to replace d minus 1 y. After replacing these substitution in homogeneous type differential equation, what we will get? We will get linear differential equation with constant coefficient in y and z variable, and that equation can easily be solved by calculating complementary function and particular integral. Now to understand the method, we take one example. This is in equation number 1. We can see x square d2y upon dx square plus 4x dy upon dx plus 2y equal to e raised to the power x. This is the homogeneous equation, as coefficient of double derivative is x square, coefficient of dy upon dx is x, and for solving this, as we have already discussed, we have to take the substitution x equal to e raised to the power z. In place of x dy upon dx, we replace dy. In place of x square d2y upon dx square, we replace d minus 1 y. And after using these substitution, this equation number 1 can easily be transformed in this form. And after calculating, simply we are getting this equation number 2. This equation number 2 is linear differential equation of second order with constant coefficient, and it can be solved by calculating complementary function and particular integral. This is auxiliary equation m square plus 3m plus 2 equal to 0. We are getting two values of m as minus 1, minus 2, and for this we can write complementary function as c1 e raised to the power minus z plus c2 e raised to the power minus 2z. Now second part of the solution, particular integral, formula is 1 upon fd cube x. Simply here it is calculated. We can replace d plus 1 d plus 2 in place of d square plus 3d plus 2. Now simply using partial fractions method we are getting this equation number A. And now we have to solve these two parts, and for this we have one formula. 1 upon d minus alpha qx is e raised to the power alpha x integration e raised to the power minus alpha x qx dx. So from equation number A we can write this term equation number B. We have applied the above formula here and now we have to solve this integration part, and for this we are replacing e raised to the power z as t. And after taking this substitution, this equation number B will reduce in this form e raised to the power minus z integration of e raised to the power t dt minus e raised to the power minus 2z integration of t e raised to the power t dt. After integration, we are getting this term, and general solution can be written as complementary function plus particular integral. Now in the last part, we are just adding these two parts, complementary function and particular integral, and after simplifying, we are getting result in z variable. So in the last step, we have to put z equal to log x, or we can say in place of e raised to the power z, we will replace x. And finally we have y equal to c1 upon x plus c2 upon x square plus 1 upon x square e raised to the power x. We'll get relationship between y and x variable. So this is the approach for dealing with homogeneous type second order linear differential equation with variable coefficient. Okay, thank you.